Hello, this is AMET 104, lecture recording week 7.1. So today we're going to start a brand new chapter. The chapter is 15, graphs, charts, and numbers. We're not going to do much writing. Instead, there are a lot of visual factors, and we're only going to go over a few definitions, and I thought it would be more beneficial if I create this for the visual aspects. So chapter 15 is simply going over very fundamental part of statistics. And 15.1 is all about being able to interpret the data and produce graphs, or the other way around. You're given a graph and you need to be able to interpret the graphs. So before we do anything, let's go over some definitions. So data set. So a data set is a collection of numbers that represent all the values obtained when measuring some characteristics of a population. So here, a test score from a class, or a stock price, or things like that. You would be able to, so something like this that you see up here is called a data set. And the data point is each of the individual numbers in the data set. So in this case, each score, so 10, 11, 10, 1, this is called the data point. We will denote the n to be the total number of data points. And it's usually called the size. So in this case, in this data set, we have the total number of data point is 75. So in this case, n equals to 75. And we also called it that the size of this data is 75. So the choice of the type of data, type of graph or chart to be used is depends on many different criteria, and many of these criteria are not quantifiable. And in this case, in this section, we're only going to go over how large is the data set, and does the data represent discrete or continuous variable, and we're only going to look at that. So what is discrete variable and what is a continuous variable? So discrete variable simply means that it's countable. So a discrete variable is one in which the value of the variables can only change by minimum increments. So in other words, two different values of the variables cannot be arbitrarily close to each other. So in this case, I know the definition that I wrote down is straight from the book, and it can be very confusing, but in simple terms, it means it's countable. So when you're counting something, for example, the distance from your home to school, it's countable. It's in some unit. You can count it in miles. Or test scores, or like things that are quantifiable, we call it discrete. Continuous variable, we're not really going to look at this in this chapter. The book does go over continuous variable, but it does make the class overly complicated. So I don't think I'm going to go over continuous variables. But just to go over the definition, the continuous variable are the variables that can be in there are infinitely many values, and those values can differ by arbitrary small amounts. So you may find a lot of typos in this PDF. I made it up really quickly, so hope you understand that. So let's do this example. So this example is straight from the book. This is, I think, one of the very first examples. So here we've seen this data set before. So we call this a data set, and each score here, we call it a data point. And we know that the size of the data in this case is 11, sorry, it's 75. Excuse me. So now we're going to go over this frequency table. So the frequency table, I'm not sure if I wrote it down. I didn't. So let's go over the frequency table. This is called a frequency table of this data set. So we can see that we can simply take out each data point and count how many of each scores are recorded. And we're simply recording into this concise form. So instead of having this huge table of data, what we're doing is we're concisely grouping the same scores and counting how many students got the score of 1, how many got the score of 2 or 3, 4, 5, and we're going all the way up to the highest score, and we're simply making the table like this. So this table simply says 1 student received the score of 1, and 1 student received a score of 6, 2 students received score of 7, 6 received score of 8, 10 received score of 9, 16 received score of 10, and so on and so forth. And I'm sure you are able to verify this here. It's going to take some time, so I'm not going to go over every single one of them. But as you can see, from here, we have 1 student who have received the score of 1, and that is recorded as such here. Same as, so let's go over, how about score of 7? There are 2 students who received score of 7, and we can see, verify that there's 1, and there's also 2 here. So it's a very simple way to summarize the data in a very concise form. And even though this shows the most accurate data with their student ID and everything, but if you want to get the general idea, frequency table is, to my opinion, is a better way to show it. So table 15.2, so in this case, this table shows that the n equals 75. So we talked about that n is the size of data, or the number of data points, and the size of data is 75. So 75 scores fall into m equals 13 different actual values, meaning that there are 16 different numbers of scores here. Obviously, there are 2, 3, 4, 5 that's missing here, but we're only counting the ones that actually has non-zero frequency. So here, m represents the number of scores. So let me just write it there. So different actual values. So yes, in this case, they say 1, 6, 7, and so on and so forth. If we think of the actual values as bins where we can place the data, we get a graph such as the one shown in the figure 15.1a. So this is the graph. So this is called the box graph. No, sorry, this is called the bar graph. This is called a bar graph because each data is represented as a bar, and we can simply see that from what it looks like. It's also very self-explanatory. You can see that for score 1, we have frequency of 1, or in other words, there's one student who received score 1. So we put 1 there. And for score 6, we have 1 student. For score 2, we have 2 students, and so on and so forth. And we have for score 10, 16 students received that. And that's reflecting this frequency table we have just created here. And we can see that for score 10, 16 students have received that score. And if we go back to the raw data points, we can also see that there are 16 students who received score 10. So this is just a different way to show the same bar graph, but in a relative frequency. So relative frequency meaning, instead of saying that 1, 1, 2, 6, 10, 16, we're simply taking how many percentages of the students received each score. The shape of the data, I mean, the data is the same, so the shape of the graph does not change. It's the same shape, but the scale may differ because we're now looking at the percentage of students out of the total students, as opposed to the actual raw number of students. So this is a pictogram. So this is also representing the same data, and we're simply drawing it in pictures, and everything else is the same. We can see here that we have 1 student who's received the score of 1, 1 student who received score of 6, and 1 received 24, and also 16 received score 10. Pictogram, as you can see, it's exactly the same as the bar graph we've seen before. And the only difference is that it's pictures. That's why it's called a pictogram. And we can also use the colors, as in this case, anything 10 or below, we represent it as red. From 11 to 13 is blue, 14 to 25, everything is yellow, whatever those colors represent. So here, the point of pictogram is that a graph is often used not only to inform, but also to impress and persuade. And in such case, a well-known icon or image can be a more effective tool than just a bar. So the serving, it's mainly the same thing. The purpose of the graph, a pictogram and the bar graph, they're the same thing to deliver information about some data set. However, what pictogram adds is that it catches attention. It's more noticeable, and hence it is more for the show, really. In the homework problems, you'll probably see a few pictograms and you don't really have to create anything. Most problems that you will see is being able to understand and interpret what it means. So when you see a pictogram, just simply treat it like a bar graph, whichever is easier for you. So now let's look at a different example. So this example is also directly from the textbook. So these two are pictograms, obviously, because it shows the stacks of money. So this is a pictogram showing the growth in yearly sales of XYZ Corporation between 2011 and 2016. It is a good picture to show at a shareholders meeting, but the picture is actually quite misleading. Figure 15.4b shows a pictogram for the exactly same data with much more accurate picture of how well the XYZ Corporation has been doing. So let's look at picture A and picture B. So these are actually the same graphs. So as you can see, in picture A, we have in 2011, we made somewhere in between $50 to $55 million. 2012, we made somewhere around $55 to $60 million. In 2013, we made $60 million, and so on and so forth. As we can see in picture B, we can also see that in 2011, we made somewhere around 50 to 55. And 2012, we made somewhere around 55 to 60. 2013, we made 60 millions, and so on and so forth. So you can actually see and compare that these two graphs are actually representing the same thing. These two are both pictograms or bar graphs that are showing the revenue of this corporation. So what's the difference here? So it's representing the same data, but why does it look different? And which is better? So better here is a very relative term, depending on what you want to show. But you can see that if you look at the y-axis, you can see that it starts from 50, 55, 60, 65, and so on. But on the pictogram B, it starts from 0. So what you can see is that the picture on the left-hand side is simply disregarding all the revenues below 50. And these two serve very different, even though they are they're one same data, they're serving two different purposes. If you want to show and emphasize that your company has been growing rapidly, if you are a growing business, if you are one of the newer businesses and you want to show to shareholders that your company is thriving and it's been growing, you can picture A will be a better option because it emphasizes the growth. However, if you've been around for a while and if you want to show that you've been steadily doing very well and also growing at the same time, picture B will be a better picture to show. It'll show you that you've been steadily doing very well and keep the high revenue each year, yet growing at the same time. If you compare the graph of A and B, you can see that growth on B may not be as dramatic as A, but we can see that it's steadily doing well for the past 6 years. So as you can see, the pictogram is all for the show, and this could have been done with a bar graph, but here for different purposes, different type of graphs are better. And as I mentioned before, you're not going to be asked to create something like this in your homework assignments. However, you should be able to see these two graphs and be able to understand that these two graphs are actually the same thing. So a variable does not need to be the measurable quantity. So earlier we have seen here the statistics score, and the variable was the score. And here the variable is the revenue, but it doesn't always have to be the measurable quantity. So the variables can also describe non-numerical characteristics, such as gender, ethnicity, nationality, emotions, feelings, actions, and etc. So variables of this type are called categorical or qualitative variables. In many cases, categorical variables must be treated differently from numerical variables, and you cannot add, rescale, or average categories because you cannot add, rescale, or average something that's not quantifiable. So let's look at an example. So suppose the following shows a breakdown of how a typical full-time university student like you are, well, I guess like most of you are, spending a typical weekday. So the student, as you can see from the table, you should be able to understand I think it's pretty straightforward what the table is trying to say. So the student sleeps an average of 8.7 hours and spends 4.1 hours on leisure and sports, spends 2.4 hours doing work, spends 3.3 hours doing, for education, for school, it's just studying, and spends about an hour eating and drinking, spends 0.8 hours grooming, 1.4 hours traveling, and 2.3 other things. And all these add up to be 24 because there is 24 hours in a day. So here are the bar graph. So these are not quantifiable data. The activity column, we can see that sleep is not quantifiable. Leisure, all these activities are not quantifiable, but we were still able to create the bar graph as such. And as you can see, for sleep, we spent 8.7 hours, for leisure and sports, 4.1 hours, and so on and so forth. And on the right-hand side, on the other hand, is called the pie graph. The shape explains it a lot. It's pie. It looks like a pie, and hence it's the pie graph. And I'm sure most of you have drawn something like this before back in grade school. And simply, the angle or the size of each wedge represents how much it represents the quantity or the frequency in this case. So the only difference between the bar graph and the others is that absence of numerical horizontal axis. In other words, in this case, the pie graph does not have these horizontal axis that show the difference between each but basically it's not really labeling each data separately, but this is all doing in one. So in a pie chart, the categories take the form of wedges of pie, with the size of each wedge proportional to the frequency of the category. So for example, here we can see that sleep is the largest, and we have leisure and sports, the second largest, and education and others, they followed like this. So how do you actually calculate the angle or the size of the wedge? And here is how. So in this case, we can see how it is actually calculated. So this is how you calculate it. So you get 8.7 hours out of 24 total hours in a day, and you're simply calculating that into a decimal form. And then, as we've done in the previous chapter, we know how to change that into percentage. And simply, since there are 360 degrees in a whole circle of revolution, you're multiplying the 360 by this percentage. And that, in this case, gives you 130.5. So this is degrees. So this implies that for sleep, to draw a pie graph, you are to draw a wedge that's a size with the center angle of 130.5 degrees here. And we're simply repeating this for every single category. And here is the table that's provided in the textbook. And you can see that for sleep, we have 8.7 hours. So you're taking 8.7 divided by 24, and you're multiplying 360 degrees, which is 130.5. In this case, they approximated to 130. Same as leisure and sports. You spend 4.1 hours, and you divide the 4.1 hours by 24, and you multiply by the 360 degrees to find the angle, the central angle of the wedge. And you repeat this for each category, and you should be able to come down to 360 if you add all these up. Let's do one last example. This will be the last example of the day. It's going to be a shorter class. So suppose we have a traditional scaling grade. I'm sorry, grading scale. So if you receive somewhere around 90 to 100, you're in the range of A. If you receive 80 to 90, 80 to 89, that's B. 70 to 79 is C, and so on and so forth. So so suppose in this class, let's say a statistics class, this is the frequency table that we have. Then we can see that there is one student that's receiving the grade of A, 8 students receiving B, 30 students receiving C, 26 students receiving D, 10 students receiving F. And these are actually the same data as we've seen before. It's the same data we've used so far with the 75 students total. So we know that the size of the data is 75. So instead of having each score labeled, we have now expressed the same data as grades. So instead of having, I think it was 14 different scores, we now have 5 different grades. So we have 1 student receiving A, 8 students receiving B, and so on and so forth. And obviously we can create the pie chart, pie graph, like, so for A, we should be doing 1 over 75. So that means that's 1 out of 75 students. And you multiply by 360 degrees. And that's how you calculate the A. Same as B, you do 8 divided by 75, and you multiply by 360, and you do the same for the rest. So for the F, you will have 10 students out of 75, and you multiply by 360. And by putting this into calculator, you should be able to find the central angle of each wedge if you were to draw the pie graph. So I'm going to end the class here today. We just went over a few different examples and learned different types of graphs and some definitions. Next class, we're going to do something more computational, but today I think this is good enough. Thanks for joining the class and have a great rest of the day.